In the name of Allah, who is most merciful and beneficial. Today I am going to represent midterm presentation of organic chemistry. Topic was assigned to me is alkynes. First of all, let me introduce myself. My name is Kiran Aslam. I am from BS Chemistry and my ID is 005. What are alkynes? Alkynes are the hydrocarbons whose molecules contain carbon-carbon triple bond and are called alkynes. The common name for this family is acetylenes because its simplest member is ethine. Introduction of alkynes. Alkynes contain a triple bond comprised of one strong sigma bond and two weaker pi bonds. We can see in ethine that there are three bonds. One bond, the central bond is sigma bond, and the other above and the below bond is pi bond. The sigma bond is more stronger because it lies on the axis of nucleus, while the pi bond lie above and below the nucleus axis, so they are less stronger than the sigma bond. Alkynes are stable and have more strength than the double bonds because it contains two pi bond and double bond contain only one pi bond. Its bond length is shorter than the double bonds. The bond length decreases when the S character increases. As we know, in alkanes, the S character is 25% and in alkenes, the S character is 33.3%, while in alkynes, the S character is 50%. So alkynes have greater S character, so its bond length is shorter than double and single bond. They are represented by the general formula CnH2n-2. The carbon-carbon triple bond is also called acetylenic bond. Structure and bonding of alkynes. The alkynes are sp hybridized, in which the 50% character is S and P show 50% character. They have bond angle of 180 degree and they have a linear structure. Alkynes are rod-like. The benzene is highly unstable. As I told you, its length is smaller. The carbon triple carbon bond distance is of 121 picometers, while alkene has bond distance of 134 picometer, and in alkyne the bond distance is 153 picometer. The triple bond is very strong with a bond strength of 839 kJ per mole. 839 kJ per mole energy is required to break its bond. The sigma bond contributes 369 kJ per mole and the first pi bond contributes 268 kJ per mole and the second bond contributes of 202 kJ mole bond strength. Now the acidity of alkynes. Acidity of alkynes depend upon the two factors. First is S character and second is pKa value. If the S character increases, the acidity also increases. As we know, alkynes have 50% S character, so its acidity is more than alkane and alkene. And the pKa value is inversely proportional to acidity. The pKa value of alkynes is less, so they are more acidic. When we do the deprotonation of alkynes, terminal alkynes, then the resulting anion is called acetylide ion. This is acetylide ion, and this deprotonation is take place in the presence of sodium amide or soda amide. Now the preparation of alkynes. Acetylene, the simplest member of the alkyne family, is of great importance due to its very high heat of combustion. The oxoacetylene torch is used for the welding and cutting of the metals. Alkynes are prepared by the following methods. There are two methods for the preparation of alkynes. First, by introducing a carbon-carbon triple bond in a molecule, or by increasing the size of a molecule that already contains triple bond. First, alkylation of acetylide ions. When we do its alkylation, it will convert into, for example, when we do the alkylation of acetylide ions, it will, in the presence of methyl halides. It will convert into alkyne through E2 mechanism or through SN2 mechanism. It will produce elongated alkynes with the elimination of alkene. Then the addition of acetylide ion to carbonyl groups. When we treat acetylide ion with the carbonyl, this lone pair of the carbon will attack on this carbon of the carbonyl group, and this bond will shift on the oxygen. And then in the second step, we will do its protonation. This negative charge of the oxygen will attack on the hydrogen and it will convert into acetylenic alcohol. By the cracking of methane, when we do cracking of methane, it converts into alkyne with the elimination of hydrogen gas. Carbide process. Acetylene is prepared on industrial scale by the reaction of calcium carbide with water, and the calcium carbide is prepared by heating lime with coke at a very high temperature. This is calcium carbide, and when we treat it with water, we obtain acetylene with calcium hydroxide, which is known as lime water. Then by the dehydrohalogenation of dihalides. There are two types of dihalides, cis dihalides and jump dihalides. In cis dihalides, the halogens are attached on the same side of the carbon atom, but in a jump dihalides, the halogens are attached on the opposite side of the carbon atom. From both we can obtain alkynes. Molten KOH or alcoholic KOH at 200 degrees Celsius favor an internal alkyne, but sodium amide at 150 degrees Celsius followed by water favors a terminal alkyne. This is the mechanism of dehydrohalogenation of dihalides. First, the hydroxyl group from KOH will attack on the hydrogen atom of the first of the one carbon, and this carbon hydrogen bond will shift here and it will convert into double bond, and the bromine of the second carbon will be eliminated. And then in the second step, again the hydroxyl group attack on the hydrogen atom of the other carbon, and the carbon hydrogen bond will convert into this triple bond, and then this time the bromine of the other carbon atom will be removed, and this reaction takes place at 160 degrees Celsius and it will convert into alkyne by the alkylation of terminal alkynes. When we do the alkylation of terminal alkynes, we also obtain alkynes. Now we will discuss the addition reactions of alkynes. First, reduction to alkanes. When we do hydrogenation of alkynes, they are converted into alkanes in the presence of platinum, palladium or nickel. The hydrogen, this triple bond will be break into single bond, and the hydrogens will be attached with both these carbon. Addition reactions of alkynes like hydrogenation to cis alkenes. We can prepare cis and trans alkenes from the hydrogenation of alkynes. We will obtain cis alkene if we use the catalyst Lindlar's catalyst, which is palladium barium sulfate. It will when we treat the alkynes in Lindlar's catalyst, then it will be converted into cis alkenes. And when we treat the alkynes with metal ammonia, then it will be converted into trans alkenes. Then the addition of halogens. When we add halogens into the alkanes, it will give a product which will be a mixture of cis and trans isomers. Addition of hydrogen halide to alkynes. Hydrogen halide adds to alkyne just as it does to alkenes. When we add hydrogen halide to terminal alkynes, we will observe Markovnikov orientation. In Markovnikov orientation, the negative part will attach to that carbon which will have least number of hydrogen atoms. Here this carbon has no hydrogen atom, so this negative part will be attached with this carbon. Now we will see its mechanism. First, this pi bond will attack on the hydrogen atom or proton, it will convert into double bond and it will form vinyl cation intermediate. This is the intermediate stage of this reaction. Then the negative part means chlorine will attack on this carbon atom and it will convert into alkene. Then the hydrogen of alkyne to aldehyde and ketones. We do its hydration in the presence of mercuric ion catalyzed hydration. First we will obtain enol and then enol will convert into ketone. We will see its mechanism. First, the pi bond will attack on the mercuric ion. Mercuric ion will attach with this carbon atom and here positive charge will come because it is electron deficient. In the next step, the hydrogen molecule will come and the negative charge at the lone pair of the oxygen will attack on this carbon atom and will attach with this. Now it will obtain positive charge. Then in the next step, again the water molecule will come and the oxygen will attack on this hydrogen atom and this bond will shift here. It will become vinyl mercuric alcohol with the elimination of hydronium ion. Then in the next step, this hydronium ion will remove the mercury ion from here and it will convert into enol. As this is unstable, so it will convert into ketone by the following mechanism. The double bond will attack on the proton. This hydrogen will attach with this carbon atom and then the water molecule, the oxygen will attack on the hydrogen and this bond will be shift between oxygen and carbon and it will change into double bond. So in this way we will get ketone. Next is hydroboration oxidation of alkynes. Hydroboration of alkynes with diisoamyl borane result in the formation of vinyl alcohol with anti-Markovnikov's orientation. When we treat it with diisoamyl borane, it will form vinyl alcohol. And then the vinyl alcohol is tautomerized to an aldehyde. So we will see its mechanism. In the first step, this group will attach with this carbon atom. It will form vinyl borane. Then this vinyl borane will become enol in the presence of hydrogen peroxide or sodium hydroxide. This will be replaced with the hydroxyl group. Then in the next step, the hydroxyl group will come and it will be converted into aldehyde. The next is permanganate oxidation of alkynes. When we treat alkynes with permanganate under neutral conditions, result in the formation of alpha diketones. We will obtain diketones when we treat the alkyne with KMnO4 in the presence of neutral conditions. It will convert into 2,3-pentane dione. Then terminal alkynes are cleaved similarly to give carboxylic acid and carbon dioxide. When we cleave terminal alkynes, it will convert into carboxylic acid and carbon dioxide in the presence of KMnO4 or alcohol. Then ozonolysis of alkynes. Ozonolysis of an alkyne gives products similar to those obtained from oxidative cleavage by permanganate. We will obtain carboxylic acid if we do the ozonolysis of alkynes in the presence of water. The hydration of phenyl gives acetophenone. When we do the hydration of phenylacetylene, we will obtain acetophenone. Physical properties of alkynes. The physical properties of alkynes are same as those of the corresponding alkenes. The lower member are gases. They show increase in physical properties with an increase in chain length. Means their melting point, boiling point, densities increases with the increase of chain length. Melting point and densities of alkyne is somewhat higher than those of alkenes. The terminal alkynes have lower boiling points than the isomeric internal alkynes. which can be separated by fractional distillation. They are less dense than the water. They are insoluble in water but are soluble in organic solvents which have low polarity. Now, chemical properties. A carbon-carbon triple bond is less reactive than the carbon-carbon double bond, but it is more reactive toward nucleophilic reagents. Due to acidic nature of the acetylenic hydrogens, they can undergo some specific reactions which alkenes do not. So that's all from my side. Thank you.